Well, thanks again for coming. Today's topic is still automobiles, so we'll finish automobiles today and then enjoy the break. Before I go back to automobiles, though, I told you, I think last time, I mentioned all these advertisements that come out about now for glorified space heaters, so I couldn't resist showing them to you. One year I collected a bunch of them. And what I want to do this. Yay! So, new model ship. Here's the important stuff is here. The guy from Home Improvements, which show I never watched, so I don't know any. Anyway, but it's fancy stuff. He's got a electricity ignites powerful Sylvania infrared lamp and patented chamber. They're basically the same as a toaster. You plug it in, heat goes into the room by conduction, convection, radiation. There may be some slight improvements on it, but some miraculous thing. No, it's just buy 100 watts of electric power, you get 100 watts of electric heat. Here's another one. Now, why it's so appealing to have the people who made this show up in a horse and buggy, I don't know, but everyone's knocking down the doors to get hold of these heat surge devices. Wow, they're so great. They have an LED flame. So it's so safe, all your pets and babies can be there and whatever. And what I wonder about is, this comes with a great coupon, $227 off before it expires. It expires 2 days from today's publication date, which is 2002. I wonder whether they'd still accept the coupon. I'll bet they would. Okay, so any questions why this is fun and games? Or, well, whatever. All right. It is true that having really hot electric filaments right there in the middle of the room is kind of dangerous. And so probably some of the better space heaters protect you against the actual 1,000 degree filaments. But otherwise, they just turn electric power into thermal power. There's nothing magic about them. All right. Having done that then, back to automobiles. And really this slide here is just a summary sort of the idea that heat pumps and heat engines go hand in hand. And yeah. Wow, I'm famous twice. Thanks. I could put the slide on both and disappear altogether. So heat pumps and heat engines are sort of the reverse of one another. And along with that, they have sort of this, there's a symmetry also in their efficiency. And efficiency, it's not in terms of it's not energy efficiency in the sense that energy is created or destroyed, they make more or less. Energy is energy. It's conserved quantity. You can move it around. You can move around thermal energy, or you can let thermal energy move around as it wants. But there are issues of efficiency that come up when you try to move it strategically. And for a heat engine, so the first entry in here, heat engines, of course, have to live under the law of entropy. What they do is they allow heat to flow from hot to cold, and they divert a fraction of it and turn that fraction into work. And the fraction, because they can't reduce the entropy of the world, they have a limited fraction they can convert into work. And the fraction becomes larger as the temperature difference between the hot and cold becomes larger. And the reason for that is hopefully fairly understandable. The bigger the temperature difference between the hot and cold, the more entropy that would normally be created in letting heat flow from hot to cold. Separate the temperatures more and more, you get more entropy with every joule of heat flow. So you can divert 1 in 10 joules, for example, and turn them into work. That will reduce the amount of entropy that is created by this process from letting heat flow from hot to cold, because first off, you've taken away one of its joules of energy that would in flowing would create a lot of entropy in the cold object. So that's part one. And even worse, you turned it into work, and that reduces the entropy still further. So if you're going to divert some of the thermal energy and turn it into work, you better make sure that you're creating a lot of entropy in the process of letting heat flow, because otherwise you're going to be violating the law of entropy. Is that followable? Are you okay with that? You're plucking off, in effect, some of the thermal energy as it's going, doing the nasty job of turning it into work, which by itself creates order and is forbidden. But if you make enough disorder by letting heat flow from hot to cold, you're covered. It works out okay. Well, you can divert more of the thermal energy and turn it into work as the temperature difference between hot and cold gets bigger, because you're getting more entropy with every joule that actually completes the whole journey from hot to cold. Questions about that? Have I said it adequately? Okay, in the other direction, so the efficiency of a heat engine, the fraction of thermal energy that it can turn into work, gets greater as the temperature difference gets greater. If you look at the other device, the heat pump, where it's moving heat from cold to hot, the bigger the temperature difference there becomes, the harder this process gets. Because the act of moving heat from cold to hot when the temperature difference is large creates a lot of order, and you got to pay for that. So you have to consume more ordered energy to run the heat pump when the temperature difference is large. When it's very small, it's easy. There's not much order created moving heat from 10 degrees to 11 degrees. Big deal. You don't have to pay much. But if you go from 0 degrees to 100 degrees, whoa, big change. You have to pay big. All right? So the point of this is, public service announcement one. When you're running your air conditioner, I've probably done this already, but I'll do it anyway. When you're running your air conditioner on a hot summer day, try to keep the temperature difference as small as you can tolerate, or you're willing to pay for, or you're willing to consume the Earth's resources for. If you try to refrigerate your house on a 100-degree Fahrenheit day, you're going to consume a lot of electric power. That is really hard work for your heat pump. And furthermore, the big temperature difference gives enormous incentive for heat to come flowing back into your house by all the conventional means. Okay? For the heat engine, if you want to extract the largest fraction of thermal energy that you can on its way from hot to cold, make sure hot is really hot and cold is really cold. The bigger the temperature difference, the larger the fraction you can extract. So I started saying last time things like steam engines. They don't just boil steam like you do in a steam kettle where they make 100 degrees Celsius steam or 212 Fahrenheit steam. They boil it under pressure, so they get steam at much higher pressure, much hotter. That's the hot source. That's the hot part of a heat engine. So in going from merely 100 degrees Celsius to outdoor air, which might be 20 Celsius, that's only an 80 degree Celsius difference. It's not enough. They'll go to like 300 Celsius steam, really hot, high pressure steam, and let it move from hot to cold. They get much more energy efficiency out of this. They can turn a larger fraction of the thermal energy into work. Okay? Well, that brings us to automobiles then themselves. How does an automobile engine, how is it a heat engine? And in picking automobiles as a topic, there's so many things to talk about. I could do a whole semester on automobiles. So I'm just focusing on the engine, but you're welcome to ask any questions about things other than the engine. So it's called an internal combustion engine because it's sort of perhaps the first system in which they literally burn the fuel inside the engine instead of outside. Steam engine is an external combustion engine. They burn the fuel outside the working system. So once they had pure enough fuel, gasoline, they could just put it into a mixture with air and burn it inside a confined environment. And when that happens, they get very hot, high-pressure gas. And that's useful. And then people figured out, I think Otto was the guy who invented, presumably the name auto has something to do with Otto, O-T-T-O. But anyway, it burns the fuel in a confined space. It lets that hot burned gas do work in virtually every case, on a piston, and then it ejects the burned fuel into the air. That's the cold part of the system. And heat is flowing from the hot burned gases into the outside air, and part of it's being diverted and turned into work by this piston that's moving back and forth. The next thing to talk about, though, is sort of the mechanics of actually pulling this off. And with the exception of there's a Mazda car that runs on a rotary engine, but other than that, they're all piston-based engines, as far as I know. And knowing how your car engine works is presumably of some value to you. So I'm going to walk you through the operation of a conventional, modern automobile engine, the cylinders thereof. And just as a outline where we're going, the engine in an automobile, in almost all cases, is what's called a four-stroke engine, meaning that there are a sequence of four separate piston movements that repeat over and over again, and that ultimately produce work that runs the engine and runs the rest of the car and does whatever you need the car to do. There are engines in existence that are not four-stroke. There are two-stroke engines. A lot of lawnmowers and lawn appliances and stuff, blowers, are two-stroke engines that in effect merge pairs of strokes from the four-stroke engine. But I'll do the four-stroke engine and walk you through how it works. The old type of four-stroke engine that existed when I was a kid used a device called a carburetor, which you still hear tell of, but there are no production cars, as far as I know. There are 0 production cars that use carburetors anymore. The carburetor's job, it was a fascinating device because it uses aerodynamics and the flow of fluids strategically to mix fuel and air and to send a vapor of mixture of fuel and air into the engine already assembled. But modern cars skip that. They just shoot the gasoline right into the engine with a device called a fuel injector. So hopefully these are terms that you've heard, and I'll try to give meaning to them as we go along. Okay, so I'm going to walk you through the four strokes of a modern engine using a fuel injector. And those 4 strokes are the induction stroke, which is the stroke that will fill the piston and its chamber that it lives in, the cylinder. It will fill an empty space in that pair with fuel and air. The second stroke is called the compression stroke, which squeezes the fuel and air mixture to high pressure and density and temperature. Right between the compression stroke and the next stroke is an event where a spark plug fires and ignites the fuel and air mixture, and they burn very quickly, followed by the power stroke, where the cylinder and piston push each other apart and work is done. So this is ultimately going to be the one that runs the engine and runs the car. And lastly, the exhaust stroke, where the piston and cylinder throw out the used burn gas, and with it, some of the thermal energy that was created during the burning process gets thrown out into the great outdoors. And that's a necessary step in this operation because it's a heat engine. It's taking heat from hot to cold. It's got to dump some of the heat in the cold in order to pay for the entropy it would otherwise get rid of in creating work out of heat. Okay? So that's a preview. So here's the real story. And please ask me if I go along and you miss stuff or I don't say it right. Because this is how a car engine works. And when you go in and get your car repaired, you might as well have some clue of what's broken or what needs work or any of that. Okay? It used to be you could fix your cars. Nowadays, they're so complicated that it used to be that like, the telltale mark of probably going to end up being a physicist was you worked on your car. And you were tinkering always trying to make it better than whatever. And now, not even physicists work on their cars unless they're collectors of like old MGs and Triumphs, like one of my buddies. The modern cars are just too automated and technically you need a computer to diagnose them. Okay, so the induction stroke, and just to set the stage, this is a slice or approximately a slice through, one cylinder of a car engine. And car engines typically have multiple cylinders for good reason. And the piston is a cylindrical device. We're seeing it from the side. A cylindrical device that slides up and down inside a cylinder. And the cylinder is basically a can. It's an open mouth or pot. It's open mouth. It's open down below, but this is the closed portion of it, up and over. So the piston's moving in and out of that closed environment and doing interesting things as it moves. As it moves, it pushes on a shaft here these are the rods, and this is the crankshaft. This is an end view of a crankshaft. It's basically this piston as it's going up and down is pedaling, as though feet on a bicycle. It's pedaling the crankshaft and making it rotate. Okay? So as this goes up and down, the crankshaft rotates around and around. In some cases, it's pushing on the piston. In some cases, the piston is pushing on it. And they crank away. And connected to the crankshaft is a timing belt, which is something that you may have heard of before, that is responsible for opening and closing valves on the top of the engine. So as the pedaling is going along, the valves are popping up and down, and carefully timed, and they have to pop up and down at the right moments. Otherwise, bad things will happen. I mean, the engine won't run properly, but even worse, the piston can crash into these valves, and disaster occurs. So they tell you at some point to replace your timing belt or timing chain. That's a necessary thing, because if it breaks while the engine is running, the pistons may well crash into the valves and just destroy parts in there. Not a good event. Okay? So, the induction stroke. During the induction stroke, the piston moves out of the cylinder and opens a void above it. This blue void here is sort of empty space, which is getting bigger and bigger as the piston goes down. The engine, the crankshaft, is pulling on that piston to pull it downward. It is doing work on the piston. So this is a step of the process where the engine does work on the piston and on the fuel and air mixture. As this void opens up, two things enter this void. One is air that comes in through a valve, which pops open strategically right at the beginning of the induction stroke, and allows air to come from your air filter and flow into the engine. If you have a turbocharger or a supercharger, that air is under pressure. That's what a turbocharger or supercharger does. It compresses the air before letting it into the engine, so you get more molecules in per induction stroke. Okay? So in any case, air is roaring into this void to fill the empty space. At the same time, a fuel injector, which is sitting up here, where's the fuel injector? It's actually not really shown. It's shooting a spray of fuel, pure fuel under high pressure. It's shooting a spray of fuel right into the airflow as it enters, so that this is not just a pure air, it's a mixture of fuel and air. Okay? At the end of this sequence, that valve up here closes, the piston is sealed, the cylinder is sealed, and the piston is all the way out, or as far as it'll ever go at least, out of the cylinder, and there's as much fuel and air mixture as you can get inside that cylinder. On to the second stroke. The second stroke is the compression stroke. And now the piston, having come all the way out, pulled out by the crankshaft's pedal, the pedal's now moved through its most extreme point, and it's now pushing up on the piston. It shoves the piston up into the cylinder. All right, so the piston is moving up toward the closed end of the cylinder. The cylinder end is now truly closed. Both valves are closed. All the valves up there are closed. There may be more than two. There may be four. There may be lots of valves. Different car engines are designed somewhat differently, and they'll tout how many valves. 24-valve engine. And like, okay, yes, that's nice. So you get this fuel and air mixture up here is being squeezed. It's being compressed by the piston shrinking the volume available to that gas. And so that gas is becoming denser by virtue of having less volume for the same number of molecules. It is becoming higher pressure because with greater pressure, with greater density, you get greater pressure. And also, it's having work done on it by the piston, so its temperature is going up. And as its temperature goes up, its pressure goes up again. So its pressure is going up very fast to a very high level. Okay? So you're getting hot, dense, high-pressure gas, as yet unburned, and that's actually an issue we'll come back to. So it's still fuel and air. Then you get this moment in which the spark plug fires. And when the spark plug fires, it ignites that fuel and air mixture, which is already hot and is certainly very hot, high pressure and high density, and it burns like crazy. At which point, time for a demonstration. Burns like crazy, oh boy, okay. So, not gasoline. It's usually methyl alcohol, but today they gave me ethyl alcohol. So, some for you, some for me. No, sorry. Can't, Of course, he spills it all over the place. Makes a great fire starter. Yes, indeed. All right, if this bursts into flames over here, sacrifices here. I don't really want to go up like a crepe Suzette or flambe. Okay, so just a little bit of, put it over there, out of harm's way. Air, fuel, mixture. And you got to vaporize it. And actually, vaporizing liquid fuels into the air is a huge issue with fuel-powered vehicles. Particularly, I guess, diesel's even worse than gasoline engines. But getting a nice uniform vapor of the fuel rather than droplets of the fuel is a good thing and hard to achieve. And if the fuel droplets are still droplets and don't burn properly, they can burn to little crispy pieces of carbon, which come out as black particles. This is particularly noticeable from diesel engines. And you've all seen a truck or something that in starting up is just piping out black, sooty smoke. Those are little particles of diesel fuel that didn't burn properly and just became little charcoal briquettes. Really little, and they're not good to breathe. All right, so if I put this on gently, too many explosions as a kid. I can try to retain as much hearing as possible. So I'm going to ignite the fuel and air mixture with a spark, big spark. And when I do that, it will burn very quickly. And I put it on loosely, and it should go up. We should be launching a missile up. Ready? Get set. That was gentle launch. I didn't put it on very. Out with the bad air. I got to put it on hard once because it's more fun. Where's the air? This is the exhaust stroke, effectively. All right. See, can I do this without making a mess? That's too much. That's good. All right. The first time I put it on there, I did not push down very hard. So that once the pressure exceeded a small value, it leapt up in the air. Usually we do better. We sometimes hit the ceiling or at least get to the catwalk. This time I'm going to put it on hard, in which case it's going to have a tough time getting free of its rubber stopper down there. And when it ignites, the pressure will build up and should blow the sides out of the bottle. Okay? Ready? Get set. Ta-da! Yes. Okay, so the point of that, who cares? But really, there's a lot of energy stored in a small amount of fuel. I was putting in 2 grams of alcohol. So a tiny amount of alcohol airs around us and whatever, and you get quite a bang for that buck. So that's what's going on inside your engine in a somewhat controlled way, but there's a roaring flame going on inside the engine. It's sort of masked from view, but there it is. People do study it in ways where they use essentially transparent cylinders and stuff, and then they get to see all the flashes and burning process. Okay, so the spark plug ignites the fuel and air mixture. Yeah, it's still up there, okay. And now you've got this hot, high-pressure gas, which obviously you don't, you want to contain it. You don't really want to just let it blow things out of the side of the car. So the piston now moves out of the cylinder, and as it does, that hot, high-pressure gas does work on the piston. And this is the work that powers the car. And this is it. Everything else is the induction stroke. The engine did work on the piston to suck air in. The compression stroke, the engine did work on the piston to squish the fuel-air mixture. Those are all both losers for the engine. You can't drive a car based on those 2 strokes. The power stroke you can drive a car on. There's a tremendous amount of work done on the piston during that moment when it's being pushed out by the hot burn gas. As the hot burn gas pushes down on the piston and does do work on the piston, it's using up its energy. It's literally giving away energy to the piston. So what happens? The temperature of the hot burn gas goes down as it expands. So the compression stroke squished the fuel-air mixture together and did work on it, and the temperature went up. And then as the power stroke lets the piston come back out, the temperature goes down. So there's a peak of temperature, then a drop in temperature. And actually between the two, there's the ignition process, which takes the temperature up to a whole new territory before it's allowed to work its way down. The last stroke is the exhaust stroke. The fuel and air mixture has had work done, the piston has had work done on it by the expanding exhaust gas, just burn gas, and it's out of energy. You can't extract any significant more energy out of that hot burn gas, so you have to throw it out. So the engine throws it out. And actually that brings up a point, is like, why can't you, if the engine started with room temperature fuel and air mixture, squished it to high pressure density, burned it, and then expanded it back down to where it started from, why doesn't it just basically end up exactly where it started from, at room temperature and atmospheric pressure? Well, it can't, because the original stroke, before burning, you start with room temperature and got up to high temperature. Then you burn the fuel, which shifts the whole path to much higher temperature. So you started at higher temperature during the expansion than you did after the compression. And as the piston moves back out of the cylinder, yes, the temperature drops, but not all the way back to room temperature. The whole situation has been shifted to higher temperature. So it drops to much hot, I don't know, 500 degrees Fahrenheit or something like that. It's still plenty hot, the gas, even at the end of the power stroke. When that piston's all the way out, do you understand the problem? I want to make sure it's clear to everyone the problem. Start with room temperature gas, squeeze it to high pressure. If you then immediately unsqueeze it without burning anything, it'll go back down to room temperature. It's reversible. Up to high temperature, down to room temperature. But if you burn stuff in between, you shifted the whole curve. The whole process jumps up to higher temperature, and the expansion starts too hot for you to reach room temperature when the expansion is over. Even if you let it do lots of work on you, it still stays hot. So what do? Gosh, well, let it expand more. And there are engines that do this trick, that actually let the piston go even farther out than it started. And I believe the PHYS does this. It allows the piston to go extra far out, And in doing so, it does a little extra work on the piston. But eventually, you come to a paradoxical situation or impossible situation. The temperature is still above room temperature in that fuel-air mixture, the burned gas mixture. However, the pressure has reached atmospheric pressure. You can't get any more work out of it. Even if you let it expand farther, you'd have to actually stretch it. You'd have to pull the piston out to go to lower pressure. So you're stuck. And it's fundamentally impossible to get the gas back to room temperature and atmospheric pressure. It's forever been shifted away in an intractable way. So you have to throw the gas away. And this is basically the law of entropy protecting itself, saying, you got work out of this, letting heat go from hot to cold. You may not get all of that heat turned into work. You can only get a fraction. And the rest you have to throw away. And sure enough, they throw it away. So the gas that is thrown out by the exhaust stroke is still hot, still full of thermal energy that is unusable. You can't, not at least in this context, you can't do anything with it. It has to be thrown away. You can use it to keep the car warm, and they do on a cold winter day. But otherwise, it's just waste heat. It goes out to a large extent through your radiator. Why do cars have radiators? Because they got to get rid of the waste heat. And there are such things as air-cooled engines that just let the air flowing around them pick up that waste heat and carry it off. But most engines are water-cooled or antifreeze and water-cooled. And so they're liquid-cooled, and the liquid goes into a heat exchanger system that exchanges efficiently with the air. That's what your radiator does. Its purpose in life is to get rid of the waste heat. It's inevitable in a heat engine. Okay? At the end of this, the exhaust valve closes, and the whole thing repeats over and over and over again. Put new fuel and air mixture in, compress it, ignite it, let it do work on the engine, and then throw it away over and over. Any questions about the 4 strokes? Nick? Does the exhaust gas mixture damage the cylinder? No, it runs not to any important level, at least not on 1 day, 2 day, 10-day timescales. Eventually, you do start building deposits of burned junk. And so when you go and have, well, ultimately when they rebuild your engine, yes, then they worry about this kind of stuff. But sometimes you put in various mixtures or additives into your gasoline that are meant to dissolve some of the crud that accumulates on some of the parts with all the burning and movement. There's also friction. I mean, think of that piston is going in and out of a cylinder dozens of times a second. It's traveling, it's metal on metal, metal sliding against metal. This is potentially a big problem of sliding friction. So there is some sliding friction, but in order to keep this as damage-free as possible, this whole pedaling process in the bottom of the piston, that pedaling process, the bottom piston, occur in oil. That's your engine oil. When you go and have your oil changed, what you're doing is you're taking out the oil that was living around the crankshaft, the pedals, and the rods here, and the bottom of the piston. That's all swimming in oil, up and down and up and down. And you choose the oil, the oil is chosen so that it's viscous enough, and you know about viscosity, to cling to those walls and keep the metal from rubbing each other away. It's viscous enough to stay in there and not get squirted out and let the metal actually touch the metal. But it's not so viscous that it's like the piston trying to move through molasses and wasting a lot of energy to viscous problems in the fluid. So they have to pick the oil carefully. And I may have ever mentioned it at some point. The engine oils that are used nowadays are clever, smart materials. They maintain a constant viscosity even as the weather gets hot or cold. They're pretty, they stay in the engine just right across a broad range of situations. In the old days, you had to adjust your oil for the season. So there was winter oil and there was summer oil. And you had to change one for the other. It's like in the old days, you had to get snow tires. I mean, you still do in some places, but basically, people have figured out how to make various car parts that work all seasons. Okay? Yeah, Maddie. Yeah, it's not, the exhaust doesn't go to the radiator, but the walls of this cylinder and the oil tube are cooled by a liquid that goes through them. So the engine has multiple chambers in it. It's got a chamber for oil. It's got passageways for water, and water by itself would freeze, so they add a chemical to it, antifreeze, that pushes down the melting freezing temperature. Remember that? If you keep the water busy with chemicals that dissolve in it, like salt, but you don't use salt, you use ethylene glycol or propylene glycol, you manage to push down the melting freezing temperature from 32 Fahrenheit, 0 Celsius, down to about as low as you can go, as minus 40, I think, or 30, something like that. So, but that's circulating there as a coolant. It's sucking away the waste heat. It is true some of the waste heat goes out as in the exhaust gas itself. Some of the waste heat goes out through the engine walls. And the heat from the engine walls goes into this liquid, which then goes to your radiator and gets cooled down and comes back in to pick up more heat. And it's driven by a water pump, which is one of those things that breaks once in a while in your car, and then you get overheating because the water just sits there. It's not circulating in your radiator properly, and you get overheating. So these are all things that you'll encounter at some point. Oh, water pump's bad. Fuel pump's bad. Oh, we're not shooting any fuel in to the fuel injectors and so on. Blue. Yeah, okay. So Maddie's question is about basically blue exhaust that you've all seen coming out of a gasoline car spewing blue exhaust, as opposed to a diesel car's life's a little more different. But if the piston, these horizontal stripes here on the piston are one of those piston rings. They're pieces of metal whose job it is to form a seal between the piston and the walls of the cylinder so that nothing gets by them. No exhaust gases get into your oil, supposedly, and no oil gets into the burning chamber, supposedly. Okay? If the exhaust gases get into the oil, they sort of pollute the oil. And so there's equipment to try to get rid of those exhaust gases. SPV valve, I think. They try to maintain a positive pressure in the oil so that the exhaust gases don't tend to come into them. But there is a problem of oil getting into the burning area. If the oil sneaks into where the burning occurs because of wear and tear on the pistons and cylinder and the rings, then you're burning oil. The oil gets in, burns, and it doesn't burn very well, or it gets vaporized into droplets and comes out, and it becomes the blue smoke you see coming out of cars. That's a sign of wear and tear on the engine. And the solution, alas, is rebuilding the engine, replacing the rings, for example. Is that okay? Yeah, make sense? You also know about car mufflers, or the need for them. A car that doesn't have a muffler sounds pop, 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 pop as it drives down the street. It sounds like a motorcycle. Even motorcycles have mufflers. But if the muffler's bad, cars are very noisy. There are a lot of yard work stuff that's very noisy. The problem is, when they open the valve here during the exhaust stroke, so after the power stroke, remember the power stroke here. That is the power stroke. The power stroke, the piston's moving all the way out. It moves as far as it can, and yet the temperature and pressure of the fuel and air mixture, of the burned gas now, never drops to atmospheric pressure. It's above atmospheric pressure, and it's hotter than room temperature. You can't get it down to room temperature. So when they open the valve at the beginning of the exhaust stroke, the exhaust valve, to let this gas out, it's at high pressure. And it leaps out with a pop when they open the valve. Every time the valve opens, you get a pop as high pressure leaps towards low pressure. And that by itself is very noisy. So what do? They run the gas through a system that the muffler, whose job it is to smooth out the pulses in pressure, probably using primarily viscous effects, sending the air through holes and channels and stuff, so it has trouble all leaping out at once. It gets smoothed out in the process of going through all these channels. And so you get a much softer purr instead of a pop, 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 pop sound. If the muffler goes bad, then it springs leaks way upstream of the exit, and you get the pop, pop, pop sound back. Or if the ductwork from the engine to the muffler goes bad, same thing. It's all pop, pop, pop. Is that okay? We already talked about efficiency limits. What I wanted to talk about was cars knocking, because this is sort of public service stuff. Why do cars knock? You presumably have heard about knocking. A car knocks, or pre-ignition, it's also called. During that compression stroke, when the fuel and air mixture are being squeezed to high density and pressure, they're also going to high temperature. And that temperature goes up quite high, to the point where in certain circumstances, it alone provides the activation energy to ignite the fuel and air mixture. Remember we talked about activation energy? To get the combustion started, you need to invest a little energy to get the molecules to start rearranging. The spark plug is supposed to do that, but if you get the stuff hot enough by virtue of compression alone, they'll ignite on their own. And when that happens, the fuel and air mixture bursts into flames before the compression stroke is done, and before the spark plug deliberately ignites them. It's bad for a number of reasons. One is the ignition occurs in a somewhat random location within the fuel and air mixture, and the burn may not be is no longer engineered properly, and it may sort of shake things up. Instead of burning from the top down in a smooth way, it burns across the fuel and air mixture in some nasty way. That's one. The burning occurs while the compression stroke is still going on, so the last moments of the compression stroke are squeezing not unburned fuel and air mixture, but burned fuel and air mixture with much higher pressure. So the piston is suddenly pushing against this incredibly strong, high-pressure stuff. So it shocks the poor piston. And the other thing is that it's badly timed in terms of extracting maximum energy. So knocking it's jarring to the engine, the cylinder and piston. It is energy inefficient because it's consuming, because the engine's not extracting energy properly from it. So to show you that this is a real problem, there's another demonstration I can do and will do. And this one I'll zoom in on. I'll remember to use the camera for this. So this is a little plastic cylinder, and the piston is this metal piston with rubber rings on it to seal it. And the thing we burn, it's just one little piece of cotton here. So I put a piece of cotton in. So it's sitting at the bottom. Make sure I don't block this. And I am going to put the piston into place. And when I shove the piston down into that cylinder, it's not going to experience much friction, so it won't heat because of friction. But the gas inside is going to receive a lot of work. Its temperature is going to skyrocket to the point where it ignites that little ball of cotton. So what you'll see is a brief flash as the cotton burns in hot, high-pressure air. Is that okay? Ready, get set. Do it again, do it again. Oh, I heard that. Right. So this is knocking. This is that process when the fuel and air ignite before the spark plug deliberately fires them, and therefore not a desirable thing in an automobile engine. Oh, come on. All right. Ready, get set. So Again, it's ignited strictly because of the surge in temperature with compression. So this is I can come back live before I forget. So this is a real problem for cars. It limits how much they can compress the fuel and air mixture without the fuel and air mixture igniting spontaneously. The more they compress the fuel and air mixture, if they could keep it from igniting, the hotter it would be before it ignites, the hotter it would be after it ignites, and the more energy they could extract from the heat engine, because they got a hotter hot. So high compression engines are designed to really push the edge of what's possible. They're energy efficient, but they're dangerously close to igniting their fuel. So those kinds of engines need a fuel that doesn't ignite easily. And that's what high octane gasoline is. Apart from sales pitch and maybe a few additives and odds and ends, when you go purchasing gasoline and you pick 87 octane or 90 octane or 93, you're buying these different grades of gasoline, really the only thing you're getting of any importance is the ability of the gasoline to not ignite during the compression stroke. And nearly all modern production cars are designed to operate with regular gas, 87 octane. That's good enough. They do not compress the fuel and air mixtures too aggressively. They do not cause this knocking to occur in most circumstances. Some amount of knocking occurs when you're going uphill hard, when you're driving up a steep hill and you slam the pedal to the metal, and you'll hear a little sound from your engine. It's experiencing some knocking, and that's just normal life. But for the most part, modern production cars operate just great off regular gasoline. And the people who put fancy gasoline in their cars, 90 and 93 octane gasolines, at what, 30, 50 cents more per gallon, what they're getting is a better ability to hold off ignition that they don't need and don't use. They're just burning. It would be like instead of using this, I were using single malt or something. What's the point? So, public service announcement: if your car runs fine on regular gasoline, use regular gasoline. There's no point in spending for the extra stuff. You are not pampering your engine. I think, in fact, that the higher octane gasolines, because they're more, the molecules are more complex. That's how they hold off they're able to withstand higher temperatures. I think they actually have slightly less energy per gallon than regular gasoline. So anyway, you just stick with regular. That's good enough. Have a great break and see you a week from today.